Hey, hello everyone. Today we have the great pleasure to have Professor Adel Javanmard from USC to be our webinar speaker. Professor Javanmard is in Department of Data Science and Operation and Marshall School of Business, and he is an executive member of the Institute for Outlier Research in Business Committee. Previously, he was the Dean's Associate Chair. Professor Javanmard received his PhD in electrical engineer from Stanford in 2014, and his research interests are broadly in the area of high-dimensional statistics, machine learning, optimization, and personal decision-making. Adele's work has received a number of recognitions, both from academia and industry, including Alfred Sloan's Research Fellow in Mathematics, IMS Tweedy New Research Award, NSF Korea Award, Faculty Research Award from Amazon, Adobe, Google, and Thomas Cover Dissertation Award from IEEE Society. He's also a good teacher and received the USC Gold Apple Award for teaching undergrad program. Without further ado, he's going to tell us something about learning from aggregated responses today. So, stage is yours.
Okay, thank you so much for the very kind introduction, and thanks for having me. Hi, everyone. It's a pleasure to be here and to share some of my work. So today I'm going to talk about learning from aggregated responses. And this is based on a few projects and paper that has been in collaboration, mostly with Google Research. So here are my amazing collaborators. And as I will explain, the way that I got involved in this project was the problem was coming from some real data application from the ads team in Google, and then we start to dive more into the details and see like what other algorithmic contribution we can make. Okay, so to set the stage, let me start by the classical supervised learning setting and then see how the aggregation would make it a little bit more complicated. So in the vanilla supervised learning problem, the learner has access to a training data. And this training data is, let's say, n samples. Each sample is a pair of xi and yi. You can think of xi as a multi-dimensional vector that's summarizing the features or covariates, and yi could be a response if you have a regression problem, or it could be a label if you have a classification problem. And the goal here is to come up with a model that you can use for personalized prediction. So if I give you a new xi, you can predict what would be the corresponding yi. Now, the area of weakly supervised learning is the setup that the learner doesn't get to see the actual labels, but has access to some sort of surrogate labels or responses. And there are different ways on how to come up with the surrogate labels, but related to what we have in today's talk, the aggregation, the way that the learner try to fix the model is that the learner never get to see the individual labels, but you first try to partition the users into different bags. And for each of the bag, you only come up with a summary of the labels within that bag. So it could be like the average of the labels within the bag, or if you have a classification problem, that would be like the proportion of different classes. And you only reveal those summary of the labels across each bag to the learner. And of course, the learner still wants to fit a personalized model to this data. Now, the setup of aggregation and working with the aggregated data has a long history. Probably the most paradigmatic example is in voting, where you don't want to reveal the individual votes, but you just come up with like a summary of the votes for different candidates across counties or districts, and then you want to do some inference based on this summary of data. The other example is in group testing, which is very classical problem, very important, and there are tons of work on that where you have scarce data to do measurements, but you want to chase some phenomena of interest in your population. Maybe you want to chase some disease or you have some quality control problem, and you don't have enough resources to do lots of measurement. And the idea here is that you want to be smarter and group the units into different bags and test each of the bags and then try to find the source of the problem much, much faster. So this is another example of working with group data. We have also examples image acquisition where you don't want to spend too much time on capturing the images. You want to be quick. So instead of trying to get the value of each of the pixel, you want to measure, take the measurements over like a grid level. There are also examples in high energy physics that it's not my domain of expertise, but there are many interesting examples there as well. So I just wanted to highlight that. Um, More recently, there has been a renewed interest in this area. I would say mostly because of the privacy concern. The way that the SK ad networks, for instance, for Apple is trying to promise some level of privacy protection is working with the aggregated data instead of the individual data. Or this is also this practice that Google Privacy Sandbox has been trying to do, working with the aggregated data instead of the individual data. And this was like the main way that I got involved in these projects and see what's going on. Okay, so let's continue with the problem formulation. So just to be on the same page, we have a feature space, that's the calligraphic X, and you have the space of the labels or responses. And then I have M disjoint bags of samples. So each of the bag, you can suppose that it's a collection of the feature vectors, and the bags could have different sizes. So NL would be the size of the bag BL. And then for each of the bag, you only observe a summary of the responses. So this is like the aggregated response over that bag, but not the individual responses. Okay. And the goal is to learn a model that you can still fit an individual xi during the test time, and it gives you what would be the prediction for the corresponding yi. Okay, so if you want to think of the bag like schematically, this is how it's gonna work. You have different features, x1 to xnl. You don't reveal the individual labels, but you just take the average, and the learner have access to xi and also the y bar of each of the bags. Okay. So there are two problems of interest in this setting. The first one is how can we learn the model F? Notably, what loss function do we want to minimize? And if it's a non-convex optimization, for instance, how do you want to minimize the loss? And the other thing is that in some settings, the learner has some sort of authority to also form the bags. So the learner is saying that you're not going to give me the individual labels, but how about I tell you what bags I want to construct, and then you reveal a summary of the labels over the bags. Okay, so it has some authority on constructing the bags. It never sees the individual labels, but it can tell you how to construct the bag. And you can try to formulate this problem. Of course, you need to have some constraint on the bags. Intuitively, you want the bag to have some minimum size constraint, because if you have very, very small bags, then it's not really protecting the privacy of the user. But if you have larger bags, and then you are taking the aggregate, the average over the bags, the larger the bags gets, the more privacy protection you can offer. You can try to formalize this intuition through different ways. One is the notion of k-anonymity, that you want the response of the responses that are revealed to at least be the same for k of the users. Okay, so if you have a bag of size at least k, all of them are giving the same response to the learner. Okay, so it's anonymous in that sense. The other way that you can formalize it is if you put some stochasticity assumption on the data, if you have some distribution randomness on the data, you can try to characterize the mutual information between the individual labels and the aggregated responses conditional on the individual feature. And that would be like the measure of information leakage that you have. And it's easy to characterize for different distribution of the data and say, if the size of the bag is growing, this mutual information is going down, so you have less information leakage. The other thing that people have been widely using and working with to justify the privacy protection is through something called differential privacy that I'm going to discuss later in the talk. The current setting that I'm saying is not differential private. I will tell you how you can make it differential private, but there is, again, this is a delicate point that in practice, whether you want to make something differential private or not. Obviously, this is going to be a very strong notion of privacy protection. It's the worst case guarantee that you can offer. But at the same time, you have some trade-off between how good your model is performing and how much privacy protection you can offer. And when it gets into practice, sometimes what they want to comply with is the legal constraint, the contract that they have that tells you, okay, you need to work with the aggregated data, but not the individual. And as far as they can comply with those legal constraints, that would be good for the practice. But if you want to be super cautious on protecting the privacy, then differential privacy would be something very useful. But of course, you're going to sacrifice some of the model utility. Okay. But to summarize, the first part of the talk that I talked about, the aggregation, is not differential private, and we will discuss how to make it DP. Okay. The first part of the talk is about the first problem and how to come up with a model. What are the relevant loss functions that we can try to minimize? Okay. And in this part, I'm decoupling these two problems, the loss minimization and the bag construction. So in the first part, I'm assuming that the bags are constructed randomly and they have, let's say, a minimum size of K. So I randomly select the users, at least K of them, put them in a bag and reveal the aggregate response. And then the question is, what are the good loss function that I want to minimize? And then in the second part, I will fix the learning process and then see how to construct the bags. Okay. It would be good to have something unifying that combines these two parts, but as of now, we have this decoupled treatment of these two problems. Okay. So there are different ways that you can try to fit a personalized model to the aggregated data, but two of the very popular loss function that has been used in literature, one of them, I'm going to call it instance level loss, and the other one, the bag level loss. In instance level loss, what you do is that you say each of the users is coming with a feature vector xi, but I don't see the actual response for that user. I only see some average response. But what I try to do is to come up with a model that fits this xi to the average response. So my loss would be on y bar of L and f of xi. So I'm using the same response for all of the instances in the same batch. Okay? But the number of samples that they have would be the number of users that they have, right? It's just work, instead of working with the yi, I'll work with the average response. So this is called the instance level loss. And the other one that's called the bag level loss is that when you are trying to fit the model, you say, okay, I don't have access to the yi, I only see the y bar of L. So how about I try to also fit those average responses to the average prediction that they make from the model. So if your model is F, you just first compute what's the average prediction that you make over the bag, and then you try to design some loss function that says how close this average prediction is to the average responses. And this is called the bag level loss because for each of the bag, you only get one term in this optimization problem. Okay. If you have like M bags, you only have like the average of M data points here. Okay. This is called the bag level loss. And when we start working with the data, the one that was coming from the ads team at Google, the bag level loss was always working better, but it was not clear whether that's the case in all of the data regime, and in what cases maybe the instance level loss would be a better option. So the first part of the talk is I want to focus on something simple, like a linear regression, and try to understand the difference between these two losses and which of them is better. What are the trade-off that we are trying to do? And maybe we can come up with the losses that are working better than both of these. Okay. Okay, so let's come up with some notation. I'm gonna call the L of sub ins. So this is the instance level, and the other one is L of the bag level. Okay, so these are the two losses that I define. The first result that we have is for quadratic loss, and um, it's a very simple result, but it's mainly giving the main insight for this part of the work. So if you look at the L of instance in the quadratic case, you can write it as the bag level loss plus a regularization term. And this regularization is essentially the variation of your predictions across each bag. Okay. So if your model is constant over each of the bags, this R of F would be 0. But if it's making some heterogeneous predictions over the units within the bag, this regularization would be high. Okay, so the instance level can be perceived as like the bag level, but you want to regularize it to be like sort of smooth across the bags. Okay. Uh, Two things that I want to highlight. One is that when we talk about regularization in statistics, usually we think of like some sort of L1 or LP norm regularization that doesn't depend on the data. It's only a function of the model. But here, the regularization depends on the xi, but not the yi. So this is like a feature-dependent regularization. And in fact, the term regularization has been used also for this setting in machine learning literature. And the other thing that I want to highlight here, the first implication that you get if you're a statistician, you would say, okay, maybe because of this regularization, the instance level loss is giving more stability to my model. And maybe the variance would be lower, but it introduced some bias in the training process. But the bag level loss, maybe it has higher variance, but it has lower bias. And another thing to hint to this observation is that, again, the bag level loss, you only have m number of samples, where m is the number of bags. So you have very few number of samples, and intuitively, it should have a high variance when you try to fit a model only to those bag level observations. Okay. So we want to try to make this more rigorous. But before going to that, I only talked about the quadratic loss. If you have a general loss function, you can do like a simple Taylor expansion and you get the same behavior, but instead of the inequality, you have some upper bound. So you can say the instance level loss is the bag level plus some sort of regularization of the same order. Okay, so the inside, at least if you relax it to an upper bound, should carry over to the other loss function as well. Okay. Now, before getting into to the analysis and how the bias and variance are behaving for different loss function, one other thing that we can do is that, okay, once you have the form of this regularization in terms of like the variation within each bag, how about fixing the form of regularization and then playing with the size of that? So I'm going to introduce a coefficient row here, and I can try to tune this row. If you have a theory, maybe it tells you what's the right order of the row. If you have real data, you can do cross-validation. But it gives you like a generalization of the two losses, and it's going to interpolate between these two losses. If row is 0, this interpolating loss would correspond to the bag level. If row is 1, it's going to go to the instance level. But maybe you can come up with some optimal row that's working better than both of these. Okay. And this is something that we also want to capture in our model. So we want to come up with a theory for general row. Okay. Okay, so back to the simple setting that we had, but it's already rich enough to give some observation. Linear regression. The usual setup that we have in linear regression, yi is a linear form of the features, and the additive noise is Gaussian, zero mean, and it has the variance sigma score. I'm going to study this model in the proportional regime where the sample size and the feature dimension, both of them are growing asymptotically, but the ratio is going to some constant. Okay, so this gives me some room to understand the trade-off between the variance and the bias. If n was much bigger than d, then you had many, many samples compared to the dimension, and the variance would be small. So you cannot understand this trade-off. So I'm going to focus on this regime. And this psi could be any numbers. For the presentation, I'm assuming that it's bigger than 1. So you have more samples compared to the features. And that was the case for the ads real data application that we have. But in terms of theory, you can also characterize the regime that psi is less than 1, the over-parameterized regime. Okay, but psi could be any number. So you could make it a very, very large constant, or you can make it a small constant. So n and d, both of them are growing, but the size of the bag, I'm going to call it k, is going to be a fixed number. So it's order 1. Okay? And I can always rescale the model to assume that the norm of theta 0 is 1. This is just for simplicity. Okay? So as I said in the first part of the talk, trying to understand the behavior of these two losses, I'm going to focus on random bagging, that the users are randomly bagged into different groups of size at least k. The bags are non-overlapping. But when I say random bagging, I really mean that the bagging structure is independent from the data. So if you have some other side information, side data on the user, you can use that to come up with the bagging, but it should be independent from the data that you are training now on them. Okay. So how about the precise characterization in the asymptotic regime? So the performance of the model is quantified through the risk of model theta, which is like the L2 estimation error of theta hat, your estimation with theta 0. Sorry, in the, okay, question, K is the size of each bag, and it's order 1 as n and d are growing to infinity. Okay, size of the each bag. So the number of bags would be roughly n over k. And we can decompose the risk function into bias and variance. The first part, the first theorem that I'm gonna give is on a precise characterization of the bias. So you can characterize the asymptotic limit of the bias and see how it depends on different things. So forget about like the equations and just see what are the relevant factors that are contributing to the bias. The first thing is that, okay, this alpha star is a fixed point of this equation. And this equation has a couple factors in it. Rho is how you want to interpolate between the bag level and instance level. And it could be any number between 0 and 1. So you can characterize all of the interpolating losses in between. Psi is n over d. So this is sort of like the so 1 over psi would be the overparameterization. Psi is the number of samples over the feature dimension. How many samples you observe, how many measurements you have for each of the dimensions. Okay, and k is the size of the bag. So all of these things become important when we are characterizing the limit of the bias. But one thing that is important is that the noise variance sigma squared that we had in the previous slide, this one, this doesn't show up in the bias. It's something that's important for the variance, but in the bias characterization, it's not going to be an important factor. It's not relevant. Yeah. And we also have a precise characterization of the variance, again, in terms of like the fixed point equation of like a system of two equations that we have. And here the variance would also depend on sigma square, the measurement error or the noise error that you have, and also the other factors like the n over d or psi that we had, and also rho and the size of the bag. Okay? So we have like a precise characterization of both bias and variance. And with that, we can try to understand how the model risk is behaving as we play with these different factors. So let's look at some of the result that we have, like the simulation. So the solid line are the theoretical line that we get from like the two theorem that I mentioned, and the dots are what we get from the simulation. So you see that when D is like 100, we are already having like a great match between the experiment and also the theory. So although it's an asymptotic things, as far as you are a couple hundred in the feature dimension and the sample size, it should be a great match. And then I'm trying to see how the risk would behave as I'm changing the row. And I'm for each of these plot, I'm fixing two of the quantities, k and psi, like on the first one, and then different curves corresponds to the SNR. In the second plot, I'm fixing SNR and psi, and then thinking of different values of k and so on. Okay. So the first observation is that the minimum risk is achieved sometimes at an optimal row that it's not neither of the endpoint. So it's not the bag level loss or the instance level loss, but you have some other value of row that is giving you the minimum risk. Okay, so this tells you you could have like losses that are outperforming both of the other commonly used losses in practice. And A few other things that's intuitive, but it's good to capture also in the plots is that as you increase SNR here is the size of the model theta over the sigma square. So how much strength your model have compared to the noise variance. The higher SNR, it means that you can come up with a better model. And you're going to see that as I increase the SNR, as I increase the SNR, the value is going down. Okay, the risk is going down. The second plot is on roll of K. So as I increase K, I'm only giving you the aggregate response over larger and larger size of the bag. So as I increase K, the risk goes up. Again, this is something that we would expect. And the other one is the role of psi. So if psi is large, you have more measurements compared to each of the feature dimensions, then you can do a better job in fitting the model. So as I increase psi, you see that the error is going down as well. Okay. So this gives you a precise characterization, and you can understand how different factors like the size of the bag is impacting the bias and variance. Okay. The other thing that we can get from this analysis is, as I said, in the real data application that we had, we were observing that most of the time, or almost all of the time, the bag level loss was working better. But this theory would tell us like what are the regime that the instance level loss is better than the bag level, and or vice versa. So here it's saying that if SNR is lower than some threshold, then it's better to go with the instance level loss. But if SNR is bigger than this threshold, then the bag level loss would be better. Now the exact form doesn't matter here, but let's see whether we can make some intuition for that one. So if SNR is a small, it means that you have too much variation in the data already. The measurement noise is a lot compared to the strength of the model. So it's better to come up with a model that tries to bring down the variance, maybe at the expense of adding some bias. Okay, so it's better to go with the instance level loss because it has some bias, but the variance was small. And if SNR is large, if you are above this threshold, it means that the variation in the data is already small compared to the size of the model. So it's better to try to bring down the bias of the model during the training. And because of that, the bag level loss would be better. So once you have this characterization, it's easy to come up with the insight and try to make sense of it. But before having this theory, that would be hard to understand whether you could have some sort of transition behavior on which of them is doing better. Okay. Okay, so with that, I'm gonna conclude the first part of the talk. Is there any question or should I continue?
I think there is a question from the audience in Q&R.
There was one on the side of the bag that I see it's already,
Yeah.
the SNR is defined as the square root of the, yeah, so SNR is the signal to noise ratio. It's the norm of theta 0 over sigma. Okay. Okay, so let's go with the second part of the talk. And in the second part, I'm gonna focus on instance level losses and then see what's the right way to construct the bags if the learner has the authority to tell us how to construct the bags. Okay, so why I'm focusing on the instance level loss. So before moving to the second part, let me go back to these definitions. And there is an important practical point that I want to highlight. So we talked about the statistical property of each of these two losses. But when you want to implement these losses in practice, the instance level loss is much more convenient to work with. And the reason is that these models are often trained on larger scale data, and the model itself is also complicated. So you want to optimize it in an online form, and also the data that you are getting is coming in online manner. And if you think about optimizing an instance level loss by some online SGD algorithm, that would be quite very simple, right? Because you can have like a sector that tells you what are the average responses for each of these bags, and then gives this xi, y bar to the learner. And the learner can try to optimize as usual in an online way. Okay. But if you think about the bag level loss, online optimization and the bag level loss would be hard because if you are, for instance, doing the batch SGD, you want to make sure that all of the units in the bag are showing up in the same batch in the batch SGD. Okay, because you want to see what's the average of your model predictions on the bag and then try to fit it to the Y bar. Okay, so the learner needs to have like complete understanding on how the bags are formed, like what are the units in each bag, and also get all of the instances in the bag at the same time in the batch that they receive to update the model prompt. So in practice, in summary, the instance level loss would be much more easier to work with. That's why I'm focusing on the instance level in the second part of the talk. Okay, so here, I'm focusing on instance level, and then the question is how to form the bags. Okay, before getting into the algorithm and the idea that I want to explain, um, if if you had the learner somehow, if you were able to cheat and look at these individual labels and then decide on how we want to construct the bags, which of the users we want to do in the same bag, you would probably say, okay, the users which have the same responses or similar responses, they should be grouped together. Because in that sense, the Y bar would be close to the individual labels. Okay, so maybe I want to put those users in the same bag. Okay, but the problem is that the learner never gets to see the individual labels. Okay. The idea that we want to work with is how about if we have some potential available prior. So I'm calling p hat a y given x. So this prior sometimes is available. Sometimes you need to construct this prior. But let's say you have some approximation of this distribution, y given x. So I never get to see the individual labels, but let's say I have this prior approximation. How can I come up with this prior? Sometimes you have the domain knowledge. You're working with the data in some specific domain and you have some knowledge of this conditional distribution. Sometimes you can train this prior on a publicly available data. The other example is that sometimes you can do transfer learning. So in the ads example that I said, think about these two tasks. One is you get like the features of an ad and you want to see what's the probability of click-through rate or PCTR. Okay? This is not a very sensitive task. Whether the people have clicked on the ad or not, this is not a very sensitive. This is not treated as sensitive information. But the other task that's closely related to this is the probability of conversion, or what's the conversion rate. So if I give you the attributes or the features of the ad and user, what's the chance that this guy would convert, which means that it's do like a purchase of this item on the web. Okay, so that would be a more sensitive information. But these two tasks are sort of related to each other. So idea of cooking up the prior in this setting is that use the insensitive task that's related to cook up this p hat and then use it to form the back construction on the other task. Okay? So this is the idea of transfer learning in this setting that I'm not gonna go in more detail in that. What we want to do is that if you don't have any of these luxury here and you just want to come up with some prior p hat. Okay? So we're gonna introduce something called prior boost that tells you how to iteratively improve your prior. So you can start with some random prior and then try to iteratively improve that and then use it to construct the bags. Okay, there is a question before I go with this slide. What if responses from the same bag are correlated? It could be the case. It's a very interesting problem, and I'm not going to cover it here, but maybe in the discussion we can discuss it. It takes a longer time. Okay. Okay, so again, as warm up, let's go with the linear regression to see what would be a good guideline on constructing the bags. Okay, so I'm going to introduce something called the bagging metrics. So this bagging matrix, I call it S, is of size m by n. M is the number of bags, and n is the number of users that you have. Okay. This is a matrix that's mostly sparse, and it's non-zero if bag L contains sample I. So if user I belongs to bag L, each of the rows corresponds to a bag, you have a non-zero entry here. And I'm also scaling each of the non-zero entries so that the norm of each row is 1. Okay, so it's 1 over size of the bag. The L2 norm of each row is 1. Okay. And we are saying that these bags are non-overlapping. So if I multiply 2 of the rows, it's going to be 0 because they don't have anything in common. Okay. And of course, the question is how to come up with the optimal bagging structure, which tells us how to optimize over S without getting to see the actual labels. Okay. So think about the instance level loss. In this case of linear regression and the quadratic loss, it has some simpler form. You can write it as this loss function. And what it does is that if you think about S times Y, for each of the rows, it's gonna take the average of all of the responses on that bag. And then once you hit it with S transpose, it's gonna lift it and use that average for all of the samples in the same bag. Okay. So S transpose S times Y is essentially doing what we have in the instance level, taking the average of responses and then using that for all of the units in the bag. Okay. And S transpose S is a projection matrix because the rows are orthogonal to each other. So we want to optimize this one. And what we can do is to characterize the model risk in terms of S. Okay? And you can do it like in a clean closed form. So once you have this characterization, in principle, you can say, okay, I want to come up with a matrix S that follows the structure of a bagging matrix, but also minimize the model risk. And the question is, what's the right S? Okay. But the catch here is that I don't get to see Y. And in this form, I don't get to see theta star. That's the actual model that I never observe as the learner. Okay? But if I have a prior, which means that some approximation of Y given X, the probability of Y given X, then I can try to approximate X theta star using my prior because this is just the conditional expectation of the responses given the X. So if I have that prior, I can just take the average response with respect to that prior, and that would be an approximation of X theta star. Okay. So for simplicity, let's say I know this X theta star. I don't know theta star, but I have some approximation of this X theta star. And then the question, what's the right S here? Okay. The next step that I'm going to do is instead of working with this expression that's quite hard to optimize, I want to slightly relax that and then come up with a guideline on what's a good bagging structure. So you can do some Holder inequality and then use the property of the matrix S, that this is a projection matrix, and then you come up with this upper bound for the model risk. Okay. So you see that this term is coming from the variance, and it's the minimum of the size of the bag, the number of the bags and the feature dimension, and the other one is sort of the bias that they have in the model. Okay. If I think about just the first term, how can I write it down? S transpose S minus identity times Y tilde. It's easy to see that this is like the k-means cost function. What it does is that it's trying to measure how each of these coordinates Y tilde I is deviating from the average response over the bags. So this is like the variance, the empirical variance of the responses. Or you can think of it as like a k-means objective function. Okay, so I can try to rewrite the upper bound in this form. Okay, so I want to minimize this plus sigma square minimum of M and D. And the constraint that I have is each of the bags should be of size at least K. Okay. Now, again, back to the motivating application that we had, trying to fit the model to understand the behavior of the users when you are showing different ads to them. The number of users is much, much bigger than the number of features that you are collecting for them. So n over k, this is the number of bags. The setting that we have is larger than d. So if this is the case, you are already in a good shape because I can drop this one. The minimum of m and d would be d, and you only have like a simpler optimization that doesn't have this term. Okay. You can also try to optimize when you have when you are not in this setting, but again, for simplicity and because that was the relevant regime in the application that we are working with, if m is bigger than d, we can drop this term. Okay? So we are back to a one-dimensional minimum size k-means clustering problem. So I want to come up with the bags, each of them of size at least k, and the cost function would be the k-means. Okay. Now, if you want to solve this optimization intuitively, it has some a very clean structural property. The way that you need to solve it is you need to first sort all of these yi and then try to group like the nearby responses together. So this was the very first intuition that we had. We wanted each of the average responses to be close to individual response. Okay. So you're going to sort them and then put these like the barriers of the bags in between to make sure that each of them is of size at least k. Yeah. But again, the question is how do you want to place these barriers to construct the bag? You can write a dynamic programming for this one-dimensional k-means problem, and the complexity of solving that would be order n times k plus n log n. So that would be a very simple algorithm to construct the bags in practice if I give you some prior. Okay. It also formalizes the very first intuition that we had that maybe people with the same responses should be grouped together if your ultimate goal is to try to fit the model in a supervised learning setting. Okay. You can also try to extend some of these results to, instead of linear regression, to generalized linear model that for interest of time, I'm going to skip. It's the same intuition, it's just like a more complicated math, but you are back to the same algorithm. Okay. Now, if we do this k-means clustering to construct the bags, so the learner would use this algorithm and then obtain the summary of the responses over each bag, can we provably show that it's better than random bagging? So the first result gives an upper bound if you follow this k-means bagging construction. And the second theorem would be a lower bound if you do a random bagging. So if you think about the first theorem, it's saying that the risk is going to 0 if I fix the dimension d and the size of the bag and I get more and more samples. This is ultimately going to 0. The first term is the bias, the second term is the variance. But since you are actively trying to minimize the bias of your model, which is like the objective in the k-means algorithm, both of these terms would go to 0 as they get more and more number of users, more and more samples. But if you go with the random bagging, the variance, of course, is going to 0 if you get more and more samples, but the bias would be lower bounded by some quantity that never goes to 0. Even if I increase n to infinity, you have some bias that never vanishes here. Okay, so the role of this k-means clustering in constructing the bags is trying to actively also minimize the bias. So both of these terms, bias and variance, showing to 0 as the sample size goes to infinity. Okay, so provably it works better than random bagging. And then the other part that's interesting is what if I don't have any prior available? So all of these things is assuming you have some approximation of probability of y given x. But if I don't have any prior available, what can I do? So I'm going to introduce something called the prior boost, but it's a very simple algorithm. The way it works is that you're given your data, you divide it into different chunks. And for now, I'm assuming that all of them are having equal size. On the first chunk of the data, I just do the random bagging. I randomly put the users into bags of size k. I fit the model using the aggregated responses within each bag. So I come up with a model on the first partition of the data. Then I'm going to use this model to predict the expectation of responses given x on the second batch. So I never get to see the individual responses, but I'm going to use the model that I trained on the first chunk to serve as the prior for the second batch of the data. And I'm going to construct the bags using the clustering algorithm that we had using these prior. Then I come up with the bags. I get the aggregation of the responses within each bag, and I update the model. And I do this process iteratively. So at every step, every chunk of the data, I'm going to update the model and then use it to cook up the prior and refine the prior for the next chunk of the data. Okay. So this is called the prior boost, starting from random bagging. How it works in practice. So this is a simple experiment to show the promise of prior boost algorithm. So the dots here would be if I just do the random bagging on the entire data set. Okay. So it's just one shot of model training. And you see that these are like the high MSC on this plot. But different curves here would correspond to the prior boost algorithm. So I'm going to go with different choices of K, different size of the bags. So if the bag size is bigger and bigger, of course, the MSC would be higher because you're working with like a larger bag size. But you see that all of them, the MSC is going down. So this prior boost algorithm is working effectively in practice. Okay, so one of them was for regression, the other one is for the classification. Okay, how much time do I have so I can plan for the rest?
You have 1 hour. I think we started like 5 minutes late, so I think you still have about 10 minutes to 11.
10 minutes.
Yeah,
Okay,
yeah.
great. So maybe in the remaining part, I'm gonna go with the notion of differential privacy. So I've been working with the aggregate responses, but people who are familiar with the notion of DP, this is not a differential private way. Okay, so how can we make it differential private? And there are some interesting trade-off that I want to discuss. So a quick recap on what's the differential privacy. A randomized mechanism M is, you can think of it as a function that takes the data set as input and then map them into some output space, calligraphic O here. Okay, and it's a randomized mechanism. Now we call it its epsilon DP. If I give this mechanism two neighboring data sets, so D and D prime are called neighboring if they only differ in one single example. So let's say one of them has me as one of the users, the other one, I remove myself from that data set. So D and D prime are only differing in one single example. What I want this mechanism to behave is that if I look at the distribution of the outcome of this mechanism when it's applied to D and D prime, the distribution of the outcomes I want to be similar. So intuitively, if I look at the output of this mechanism, I don't want to be able to say whether Adel was in the data set or was not. Okay, so you can also formalize it in terms of a hypothesis testing problem. Now, if these two distributions are close to each other, it's private because it's not giving me any hint whether one specific user was in the data set or not. But if these two outcome distribution are very large, then maybe I can get some hint on how to do some statistical tests to say whether someone is a member of this data set or not. Okay, so this coefficient here, e to the epsilon is called the privacy budget. If epsilon is 0, it's completely private. If epsilon is large, it becomes non-private. So this is like a privacy loss or how much budget you have to sacrifice the privacy of the users. Okay. The smaller epsilon means higher privacy. Now, how people make things to be differential private, the usual way of making it differential private is by adding some layer of noise. And this is something that we have not been doing in the aggregation, right? We are just taking the average of responses. But how people try to add noise here? A notion that's relevant is called the L1 sensitivity. So if you have a function f that's defined on the data set, you can see how much it's going to change in the L1 norm if I change one of the users in this data set. Okay, so this is how sensitive it is to each of the samples in L1 norm. Okay, and a usual way to make a mechanism differential private, if you have a function that takes the data set and reports something in RK, you just add some noise to the output. Okay, And this way you can get some sort of differential privacy. So this is like looking at the outputs of this data through some frosted glass, some noise. Okay. How much noise do I need to add to make sure that this is differential private? This is, of course, depending on the privacy budget that they have, epsilon, and also how sensitive the function is with respect to the um, one replacement in the data set. Okay. If it's a very sensitive function, then I want to add more noise. Okay. But if the function is flat, let's say it's not sensitive at all, then you don't need to add any noise, right? Because it's not going to change the outcomes already. Okay. So this is called the Laplace mechanism. And this is one of the like the common way of ensuring differential privacy. Now, in the talk, I was only focused on protecting the privacy of the label. So I was assuming the setting that the X's are not containing sensitive information, but the action of the users, whether they purchase the product, whether they click on something, whether they, I don't know, took some decision given all of these contextual information, that was a sensitive information. And the right notion for that is something called label differential privacy. So it's the usual differential privacy context, but here you're only focusing on the labels. So when I define two data sets, D and D prime, to be neighboring data set, it means that they differ in the label of a single example. Okay? So this is like a more restrictive setting when you only care about the privacy of the labels. And this is the more relevant one for the aggregation setting that we have. Okay, okay. So how can we make the aggregation framework to be differential private? The very natural thing to do is after I compute the average response within each bag, I'm going to add a Laplace noise to the average response. How much noise do I need to add? Um, of course, it depends on what's the privacy budget epsilon that I have, and also the sensitivity of the aggregate responses to each of the individual labels. Okay, so if I assume that all of the labels are bounded by B, the sensitivity would be B over K, because if I change one of the responses, the average response over the bag would change by at most B over K. Okay, so the larger bag that I have, the less sensitivity I get in this setting. Okay, and here is the interesting question. Let's say I fix the privacy loss. So I tell you epsilon should be 2, for instance. So this is how much privacy loss I want to have at most in this layering problem. What's the right way to ensure this differential privacy? Or in other way, what's the right size of the bags here? Why do I say the size of the bag has some trade-off here? Because if I go with larger bags, I get coarser measurements, so the model quality goes down. Okay, but larger K, larger bag size means that my average responses are less sensitive, so I can add smaller noise when I'm making it DP. Okay, so on one hand, larger bags are not good because the model quality is going down, but the other hand, larger bags are good because they're making the aggregate responses to be less sensitive, which means that you need to add less noise when you're making it DP. And the question is, what's the optimal size of the bags? So if I get that the optimal size of the bag is not 1, then it's saying that if you want to ensure epsilon DP, maybe it's better to first aggregate responses and then add noise on top of it, instead of just adding noise directly to each of the individual responses. Okay, so this was the interesting question that we wanted to see, whether the optimal K is something different than 1. Okay, and here is the empirical demonstration that we got. The y-axis is the log loss, and the x-axis is the sample size. And then different curves corresponds to different size of the bag. Okay, so I'm fixing the privacy loss epsilon to be 1, and I want to see what's the optimal K for different size of the n, right? So if n is within this range, the optimal K, if you look at this curve, the optimal K is, I think K equals 2 here. And as I increase n, the optimal K here would change to 4. Here it's going to be 8. In this range, it's going to be 16 and so on. So the optimal K is also growing as I give you more and more samples. And from this plot, a good guess could be like the optimal k is going like log of n. Okay. So obviously it's saying that if you want to make it DP, maybe it's better to first group them into bags of this size and then try to add Laplace noise on top of that. Okay. And the other thing is that the crossover points for optimal K gets further apart as n is growing. Okay. So as I increase n and n, the optimal K would remain optimal for a larger range. Now, can we prove it in theory? This is something that we have not done, but that would be interesting to, at least for some of the simple models, characterize the optimal K and prove that it's not how it's going to behave with the sample size and like the feature dimension. Okay. So I think I have 5 minutes or less than that.
Yeah, 5 minutes. Yeah.
5 minutes. Okay. I'm not sure if I should go through the third part or not. Okay. I think maybe I skip this one and go to the summary because I'm not sure if I can cover this. Okay. So we talked about the learning framework from aggregated data, and we said that it has a long history back from like group testing in voting and image acquisition and so on. But recently there has been a resurgence in this area because of the privacy concern that you want to work with the aggregated data instead of the individual data. In this talk, we only focus on aggregated the labels. So we were treating the feature vector to be non-sensitive. But you can generalize some of this work to the setting that both the feature vector and the labels, both of them are having some sensitive information and you want to protect them. The usual way that people talk about privacy protection is through differential privacy, but that's a strong notion in worst case. Maybe a more moderate approach to privacy protection, especially if you have some stochasticity on the data, is to try to work with the mutual information. So you want to capture this randomness of the data when you are providing guarantee. It's going to be more relaxed because this is not the worst case. And the aggregation could be justified in terms of the information leakage, in terms of the mutual information. Okay. We formulated this problem as the first part, how to come up with a loss function that you want to minimize and fit the model to the aggregated data. And the second part of the talk was if the learner can choose what users should go into the same bag and then get a summary of those bags, what's the right strategy for the learner to construct these bags? For the first part, we talked about the instance level and bag level loss and some interpolating loss that combines both of them. And we came up with a precise characterization of the bias and variance. And it sort of demystify on how different factors is going to impact the bias and variance of the model. The second part of the talk, the back construction, we talked about the prior boost. And the high level idea was that you do some data partitioning. On the first part of the data, you do just a random bagging to fit the model using the aggregated responses within each bag. And once you have the model on the first chunk, you can use it to cook up your prior on the second batch of the data. You get the aggregate responses within the bags, and you repeat this process and refine your prior as you move on. Okay. And we prove like theoretically that's going to be definitely better than random bagging because the random bagging has some non-vanishing bias in the model. Okay. The other part that I didn't get to talk about is how to achieve the optimistic rate for this framework. So I'm gonna maybe just point to the paper, and maybe in the discussion we can talk more on that. So this is the optimistic rate on the Coles paper. Okay, thank you so much.